In this section, we're going to take another Calc 1 concept that we studied at length in Calc 1 and extend it to 3 dimensions. So in Calc 1, we had lots of situations where we were given some sort of a function, and then at a particular point on that function, we were asked to find a tangent line to the function at that point. And the idea was that near that point, the tangent line does a really good job of approximating that function, but then the further away you get from that point, the less of a good approximation that line became. And so to extend this same idea to 3 dimensions, we're talking about, rather than a curve, we're talking about a surface. And then rather than a line, we're talking about a plane. And so you can see in the picture here, what we're going to be looking at is finding the tangent plane at a particular point P. And this plane is going to be determined based on some of the ideas that we learned in the previous section. So we learned that we can look at curves on a surface that where one of the variables is constant. Okay, so the C1 and C2 that you see here are the places where we're setting X or setting Y at a particular value. And then if we do that, then we're able to find tangent lines to those curves, so T1 and T2. And then the way we define the tangent plane is it's going to be the plane that contains both of those tangent lines. Now, what we did in the previous section with this business of finding these tangent lines is we talked about how these tangent lines are related to the partial derivatives with respect to x or with respect to y. So that's what we're going to do. And in example 1 here, we're going to kind of slowly develop this idea of how we come up with this tangent plane, and it's going to be based on the fact that we're going to find these 2 tangent lines to these curves where x and y are constant respectively, and then we're going to make sure that our plane contains both of those tangent lines. So here's the function we're going to work with, and this thing is an elliptic paraboloid, and what we'll have here, move this down a bit, is we're just going to start by verifying that this point here, and ultimately this is the point we're going to find the tangent plane at, we're going to verify that that is in fact on this surface, right? And remember, that just entails me understanding that this f is the z value. Okay, so z is going to equal the function evaluated at -1 and 2, which would be 4 minus 2 times -1 squared minus 2 squared. So 4 minus 2 minus 4 is -2. So that verifies, because I get the z value I'm expecting, that yes, this is a point on the surface. Now it's asking us to find the partial derivative of f with respect to x. All right, so we know how to do that. That's just me thinking of y as a constant and then taking the derivative with respect to x. And so, of course, the 4 goes away and becomes 0. In that middle term, I get minus 4x, and then, of course, I'm treating y squared as a constant, so it just drops out. And so the partial with respect to x at -1, 2 is going to be equal to -4 times -1, plugging -1 in for x. So the partial derivative with respect to x at this point here is just 4. Now on the next page here, we're going to do one more thing with this. So let me just write the answer we got on the previous page there. So it says in part B, we want to find the equation of the tangent line to the curve C1, which is the intersection of the surface and the plane y equals 2. In other words, we're holding y at 2, right? We're freezing that, and we're saying, what curve do I get when I hold y at 2? And then we want to come up with the equation of the tangent line for that. So before we actually find this equation, let's take a look at the picture. So here is that surface, and you can see here, this is the curve where y is frozen at 2, right? You can see y is 2. And so this is the curve that we are generating. And so what we want to do is find the tangent line to this curve at our point. And so here's the picture of that. So this is the line whose equation we're trying to find right now. Okay, so I want us to think in 2 dimensions for just a moment. So I want you to pretend that this curve and this line are existing in 2-dimensional space, just like we did back in section 11.3. So if that were the case and we were ignoring y, we kind of pretended that y wasn't a variable that exists, because we can do that because y is frozen at 2. So in this problem, essentially, I want us to do this like it's Calc 1. So what would we do in Calc 1? We would take z minus the z value we're at is equal to our slope times x minus the x value we're at. But the slope we know, right? We learned that the partial derivative with respect to x is this slope right here, right? The slope of that line. And so our equation is just this, right? Because what does the partial with respect to x tell us? It says if y is frozen, how is the function changing? How is the z value changing as x varies near that point? All right, so there's that line. Now we're going to do the same thing doing the partial derivative with respect to y. So the partial with respect to y is negative 2y. And so the partial with respect to y at negative 1, 2 is equal to negative 2 times 2, which would be negative 4. And similarly down here, so now we're freezing x in place. Again, we'll go back to our picture here. So we want to freeze x in place, and here's x frozen in place. So we've just put in another curve, and you can see this is where x is frozen at negative 1. And then we're going to find, I'm pretending that it's all just 2-dimensional, we're going to find the equation of that line right there. So you can see we have these 2 tangent lines that we're going to come up with. And so, of course, m2, what is that? Well, that's got to be our negative 4. So we have z minus negative 2 is equal to negative 4 times y minus 2. All right, and now finally in part F it says use parts C and E above to find the tangent plane to this surface at the point 1, 2, negative 2, and put it in this form. Now, first of all, putting a tangent, this is clearly a plane, right? Because remember, our equations of planes have an x, a y, and a z, and they're just multiplied by constants. And then you also have you have a constant value if you were to kind of combine all your like terms. But there's no reason I couldn't write it out like this, right? So now what I want us to understand real quick is if we're talking about our tangent plane, and we know our tangent plane has to contain this original point, right? And it clearly does, because if you plug these in for x, y, and z, you get 0 equals 0, so this will work. But then as I move away on the tangent plane, I want us to think for a moment about moving away along one of those tangent lines that it's supposed to be containing. So in other words, as I zoom in a bit here, as I move along these red lines here, right, what's happening? Well, what's happening is if I move along the red line that where y is equal to 2, then the equation of the tangent plane becomes just this right here, right? And if you look at this equation, this is identical to this one here. So it must be that our A is actually equal to 4. And then conversely, if I go along the curve where, or excuse me, go along that line where x is frozen at -1, then this one goes away and we just have b, and so that must mean when you look at this compared to part E, this must be -4. So when you write a tangent plane in this manner, that a and b constant have to be the partial derivatives with respect to x and y respectively at that particular point. So here's how we would just wrap this up, is we would just note that a must equal the partial, let's see here. Oh, sorry, there's a little typo. I didn't even notice that. That 1, of course, should be -1. So in case that was confusing you there, that's a -1. So the partial with respect to x at -1, 2 has to be our a, and we know that that is 4. And we know b is the partial with respect to y at -1, 2, which is -4. And so here's our plane. And of course, I can clean this up, and I should. So z plus 2 equals 4x plus 4 minus 4y plus 8. So z is going to equal, moving all those constants to the other side, 4x minus 4y, and looks like we'll get plus 10. All right, so now that we've derived, this general form here and realized that a and b really just should be the partial derivatives with respect to x and y, now we can kind of give a general equation that we can always rely on and not necessarily have to develop it in such a long-winded way. So if you want a tangent plane at this point, just take z minus the z value of that point equals the partial of x, evaluated at those x and y values, times x minus the x value at that point, and then same thing with the partial with respect to y, and the y minus the y value at the point. And going back just real quick to that picture, if I type that, and I know that, I typed that equation up here, you can see it right here, 4x minus 4y minus e plus 10. That's just how you have to type it in for that particular type of plot here. But you can believe that that's in fact the plane. And so here's what we get. There's my plane. That looks like a kite in this case because of how it cut off. But here's the plane. It contains both of those tangent lines. All right. So now let's do an example kind of more like you would do in homework where you don't have to necessarily develop all that, but you can use this formula here. So it says find the tangent plane to the surface given by that equation at the point -1, -1, 1. All right. So notice first of all that they're using the notation z equals instead of f of xy equals, right? That's no problem at all. And just note that up here in this formula here, we're talking about the partial with respect to x, but remember, we can also use that notation, right, when we're talking about partial with respect to x. Okay, so when we take the partial with respect to x, we're thinking of y as a constant, but I really do have the product of functions of x here, right? So I'm going to have to do the product rule. So the derivative of x squared times e to the x minus y plus x squared, and then the derivative of e to the x minus y is just e to the x minus y, right? Because if I had e to the x minus 4, then the derivative would be itself, right? Because with the chain rule, the derivative of the top here is just 1. So that's going to be my partial of z with respect to x. And the partial of z with respect to y. Now this I do not have to think of as a product rule because y only appears right here. So x squared is just like it's a constant. E to the x minus y. And then the only thing I have to remember is because the y is the variable and there's a negative in front, when I do the chain rule of what's up here in the argument, I'm going to get a negative 1 for the derivative of that. So we get negative x squared e to the x minus y. All right. But of course, I want to evaluate these at these specific x and y values here, right? So I'm going to take the partial of z with respect to x, evaluated at negative 1, negative 1. And so 2 times negative 1, e to the negative 1 minus negative 1, plus negative 1 squared, e to the negative 1 minus negative 1. So these, of course, e to this stuff is just e to the 0. So we just have negative 2 plus 1. So negative 1 is what we get out of that. Partial of z with respect to y. Negative 1, negative 1. And so that's going to be negative 1 squared. So we also get a negative 1 there. All right. And so what is this thing telling us to do? It's just telling us to z minus the z value of our point equals the partial with respect to x at those x and y values times x minus the x value at our point, and then same thing with the y. And of course we can clean this up. Let's move this down a bit. So clean this up, and we've got negative x minus 1 minus y minus 1. So z is equal to negative x minus y minus 1 when we clean all that up. And so let's just take a look at the picture of this one as well before moving on. So here's our surface. And so here's the point on our surface that we're finding the tangent plane at. And so I obviously already did this, but if I go ahead and plot that plane, here it is. And this one's kind of an interesting one in that I think we could all agree that this tangent plane is doing a really good job of approximating the surface at that point. But over in certain regions, right after that point, the surface pops up above the plane. And then in other regions, it dips down below the plane, and yet still the plane is a really close approximation there, right? And that's different than this one, where this one's a little more kind of what you would visualize with a tangent plane, kind of sticking that flat surface, kind of gluing it to the surface there. But both are the tangent plane, a good approximation of the function at that particular point. Now in Calculus 1, you took the idea of this tangent line to a function at a point and gave it this name, the linear approximation, okay? Because that's really what a tangent line is. It is a linear function that approximates your function as long as you're close enough to the original point. All right, so here, I just want to remind you of what that formula is. So the linear approximation to this function at the point A is just going to be this value f of a, okay, which is right here, plus the derivative at a, right, which is our tangent slope, times x minus a. That is the equation of this line, okay? And if we did the linear approximation and plugged in an x value that's really close to a, it does a pretty good job of approximating the function. Whereas if I pick something way out here, it might do a pretty poor job of approximating the function, right? So that same idea here can apply to this idea of tangent planes. So, and you'll notice the similarities, right? So what did we do up here? Let's just capture this in our brains. We took the function at our point, or at our x value that we're interested in, plus the derivative there, times x minus a. All right, well, what are we doing down here? To get the linear approximation, we're taking the function at ab plus the partial derivative with respect to x times x minus a plus the partial derivative with respect to y times y minus b. So it's just an extension of that formula we were just looking at. And the other thing that I would point out to you is this as well. We just introduced the idea of the formula for a tangent plane. We'll understand that this is just a z value. This is just a z0 value. This is, well, the partial derivative. But then this a and this b, right, they're just different. I'm giving them the letters a and b in this particular formula, but this is just the x0 and y0 that we were talking about before. So just understand, when we talk about linear approximations, all we're talking about is a tangent plane. We're not talking about anything different at all. It's just we're kind of expressing it differently and getting the z all by itself on the left side. All right, another thing that you should notice here is, just like with the line up there, the closer we get to a, the better the approximation. Well, the closer we get to the point on this surface that we're finding the tangent plane to, the better the approximation is. So you can see the x and y scales, as I shrink them down, as I go from left to right, the plane does a better and better job of approximating that surface. All right, so in example 3 here, they want us to find the linear approximation for this function at negative 1, 4. And we want to use that to estimate the function really close to negative 1, 4 at negative 1.05, 3.95. So we know that we need to find the partial derivatives. Right, so that would be negative 8x. Partial with respect to y is negative 16y. Now, that evaluated at negative 1, 4 is 8. And that evaluated, at negative 1, 4 negative 64. Okay. Now, what else do we need, right? So we need those partials, but we also need to know what is the function. What is the function at negative 1, 4 itself, right? What's kind of our starting value there? And so that's going back to the original function. And when I crank that out, I get negative 120. So what we know is that the linear approximation of this function at xy at the point negative 1, 4, right? And let me just write out the formula real quick. Negative f of negative 1, 4 plus the partial with respect to x at negative 1, 4 times x minus negative 1 plus the partial with respect to y at negative 1, 4 times y minus 4. But we know these three things, so we can plug those in. So my linear approximation formula is going to be negative 120 plus 8 times x plus 1, and then minus 64 times y minus 4. Okay, and I'm just going to leave it there for now. I know I could simplify things a little bit, but this is actually in a pretty good position for me to be able to demonstrate what's happening here. So if I now go ahead and plug in negative 1.05, 3.95, then we end up with negative 120 plus 8 times that minus 64 times that. And the reason I kind of wanted to leave it this way is so that we can really see here why it is that we're getting a pretty good approximation. This is the function value at x equals negative 1, y equals 4. We are moving just a little bit away, right? We're moving 0.05 away in the x direction and 0.05 away in the y direction. And then these partial derivatives tell me, okay, if you move a little bit in the x, what is the rate at which you should be changing your z value? Well, here it's plus 8 per unit in the x direction. Here it's minus 64 per unit in the y direction. So it's this little bit of movement times these partial derivatives that gives me the slight adjustment I have to make to get my my approximation of this function. And so this is negative 117.2. Okay. Now, that linear approximation is great, right? It gives us a chance to estimate a particular value of a function. Now, why would you want to do this? Well, in this case, our function's formula is not that hard, but what if it was a really, really complicated function? If we could come up with this linear approximation, then I don't have to do all the complicated calculations that might be involved in that function. I can use this and get pretty close to the answer. Now, in this, because of the fact that our function is pretty friendly, we can definitely go ahead and plug this value in and see what we get, just for fun, so that we can see how close we actually came to approximating the actual value. When I crank that out, I get 117, 117.23. Very, very close, right? So you can really see this idea that the tangent plane does a really good job of approximating the function value at when you're near that point. Okay, last little topic here is just to address the issue of how do I even know that a function is differentiable at a particular point? And let me just give you kind of a familiar example from Calc 1 where you have a function that is not differentiable at a point. So if I had a function, let's just take an absolute value function that's been shifted around a bit. So if that's my function, and this is a, remember that you can't take the derivative at a corner, right? Just as one example where you can't take a derivative. And so we would say this function is not differentiable at A. Okay, so we know that you can't always take the derivatives of functions, and it shouldn't surprise us that with surfaces it would be the same thing. So in Calculus 1, one of the ways you can think about whether a function is differentiable or not is to first of all think of things in terms of that really a derivative is the change in y over the change in x, small change in y over small change in x. And so that would translate to this ratio here, okay? And that's approximately the derivative as long as change in x is nice and small. So another way you could think of it is this ratio here is equal to the derivative plus some error involved, right? Because it's not perfectly equal. So what that allows me to do then is if I multiply both sides of this by this delta x, then you end up with this right here, okay? And so one way to talk about differentiability is to say that the function's differentiable at a point if the error goes to 0 as delta x goes to 0. Okay, so in other words, as the change in x gets smaller and smaller and smaller, this error should head to 0. So that's going to be the kind of the crux of our definition of differentiability in when we're talking about functions of more than one variable as well. We're just going to add to it, right? So now we've got partial derivative times delta x, partial derivative times delta y, plus two different types of errors, but you can just see the analogy here, right? And we're going to say that the function's differentiable if the errors go to 0 as the change in x and change in y go to 0. And another way to put this is the definition says that a differentiable function is a function in which the linear approximation is a good approximation when x and y are near A and B. All right, now this business looks like a big mess that we don't really want to have to deal with on a practical basis. So here's a theorem to help us out for something we actually can check. Is it says if the partial derivatives exist near the point and are continuous at that point, then f is differentiable. And that's a theorem we're not going to bother to prove, but what that means is for us is if we're asked if a function is differentiable, and this is the one we found a tangent plane to earlier, remember? If I want to show it's differentiable, in this case everywhere, then all I have to do is calculate the partial derivatives. And remember, we did this already, right? So this one, we use the product rule. Oops. Use the product rule there. And then partial with respect to y was this. Okay, and so what are we looking for? We want to show that the partials are continuous at AB. Okay, well, what do I have here? I have exponential functions, right? Exponential functions. Exponentials are continuous everywhere. And I also know that polynomials are continuous everywhere. And that's all that these functions are made out of. Polynomials, 2x, x squared, negative x squared, and exponentials. So if that's all that they're made out of, then we can say, so the partial derivatives are continuous everywhere. And so f is differentiable everywhere, according to that theorem. Now, and remember, just as a reminder, what does continuous mean, right? I think our favorite definition is, can you draw the function without picking up your pencil, right? Clearly, you can draw a polynomial, right, without picking up your pencil. You can draw an exponential without picking up your pencil. And because every single part of these partial derivatives is made of polynomials and exponentials multiplied or added together, then you can conclude that the partial derivatives themselves are continuous everywhere.